In this video, we're going to start looking at series and parallel circuits. So far, we've introduced basic electrical. We've now taken a look at some of the electrical concepts like voltage, current, resistance, and wattage. We've also discussed frequency, AC, and DC. Now we want to start taking a look and seeing the way different circuits are put together and how we're going to troubleshoot these different circuits using a meter. So, the majority of circuits you work with in HVAC will be far more complex than the single switching device that we just talked about in the prior video. We have to then understand two ways circuits are designed because how you troubleshoot these two methods are completely independent of each other. We're going to start off with just a basic definition of Ohm's Law. I'm not going to beat it to death right now. You have a lot of exercises and we're going to talk more about this in the future. But Ohm's Law defines the relationship between voltage, which is represented as an E, current, which is represented as an I, and resistance, which is represented as an R. The formula for Ohm's Law is E equals I times R. And please remember, anytime you see an asterisk, that's multiplication. And Ohm's Law, using the formula E equals I times R and having 1 amp of current with 1 ohm of resistance, there will be 1 volt. So E equals 1 times 1 equals 1. Using the same formula with 0.5 amps and 100 ohms, you'll measure 50 volts. And again, that's because I times R. So 0.5 times 100 will be 50. Ohm's Law can be shown as a circle as well. Okay, so if you put it sort of in a pie chart with E at the top, then I and R next to each other, if you're looking for E, you're going to multiply I times R. If you're calculating for I, you're going to divide E by R, which is voltage divided by resistance. If you need to find resistance, R equals voltage divided by amperage, or E over I. So the easiest way to remember Ohm's Law is remember this circle. You just basically cover up the one you're looking for and either multiply or divide. Now, series circuits is one type of circuit we can talk about. Series circuit exists when there's a single flow for electrons to pass. Okay, in other words, everything must be in series, one right after the other. There's no alternates. So switches that control loads are wired in series with these loads. There's no path for electricity to flow around a switch. This is an example of a series circuit. Okay, our current comes from our source and has a single path for electricity to flow. In other words, nothing can flow around switch 1 or switch 2. There's no alternatives. The loads are also in series. B1 is in series with B2. There's no two ways for current to move. So looking at that diagram again, switch 1 is in series with switch 2, which is in series with B1 and B2. If any one of these components in this circuit is open or fails, the remainder of the circuit will not work. Loads in series split the source voltage based on their resistance. Neither B1 or B2 will be getting full source voltage. The amperage in a series circuit is the same through the entire circuit. And then the total resistance is the sum of all the individual components' resistances. The voltage drop or voltage measured across each load can be calculated using Ohm's Law for that individual load. In the HVAC industry, it is rare to see loads in series. It's very frequent to see switches and safety devices in series with loads or control devices. In this case, both switches must be closed to provide a path for electricity. In a series circuit, any open will cause the entire circuit not to work. So again, let's go back to our series circuit. To troubleshoot a series circuit, start by making sure all switches that you can close are closed. Now check the voltage at the source. Make sure you have source voltage. If you don't have source voltage, don't even bother going through further. Find out why you don't have source voltage. Now check the voltage across the first switch. That in this case, this is our service switch or breaker. We should have 0 volts because voltage across a closed switch is always 0. If I have my switch manually closed and if I get voltage across it, something is wrong with the switch. Now check voltage from the line side of switch 1. Is my conductor, is the wire from this point to this point good? If I don't have 0 volts, there's a problem someplace there. Check voltage from source to the load side of switch 1. Now there again, I'm bringing a new term, load side. That is the side of any switching device that is facing the loads. I should have 0 volts. If I have voltage here after doing my prior checks, switch 1 is bad. Go to the line side of switch 2. Again, new terminology. Line side means the side away from the load, facing the source or line. 0 volts. If I would get voltage here after completing the prior checks, I would have an open wire between switch 1 and switch 2. Go to the load side of switch 2. Okay, once again, if I have voltage here after completing all the prior checks, switch 2 is bad. And you'll note that I'm not moving one of my meter leads. I'm going across the entire circuit, okay, up to certain points. This is called hopscotching through the circuits, and we'll talk more about this in my meter video. Now I'm going to check the voltage from source to line side of B1. Again, if I have voltage here after completing all my prior checks, the line between switch 1 and switch 2 is open. Go to from source to the neutral side of B1. You're going to get some voltage. We haven't calculated how much voltage you're going to get. I'm using 60 volts in this case because I'm going to split it equally between the two loads. But this might not be 60 volts. If the load is working, we're fine. Okay? Now, if I get full 120 volts, it means that their load 1 has an open in it, or it's a bad load. Go between source to line side of B2. Again, if I get 120 volts or whatever source is, I'm going to have an open here. If I just get part of source, it's normal. It means B1 is working and I have voltage coming this direction. If I get 120 volts across all loads, okay, and B2 is working, our circuit's good. If I get source voltage, which in this case 120 volts at this point, and B2 is not working, it means we have a bad load. We have some basic things we have to talk about. Voltage across an open switch in a series circuit will always be source. So I don't care if it's 120 volts, 240 volts, 480 volts. If I have voltage at any switch, or if the switch is open, it's source. If I have voltage across a load and the load is not working, it's a bad load. If I have voltage here, okay, across the loads and B2 is not working, it's going to be a bad load. So again, voltage across an open switch or any open in the circuit is going to be source voltage. If there is source voltage across B1, in other words, at this point, if this would be the same as source, I would have an open someplace in this side of the circuit because it acts like a switch. And I'm going to talk more about that in my meter video. Do final check just to make sure you still have source. Okay, circuit's good if you come up with all those readings. When troubleshooting a series circuit, if you get source voltage across any switching device, that switch is open. I don't care whether or not you have it manually turned on, but something internal of that switch is open. When troubleshooting a series circuit, if you get source voltage across a load and that load is not operating, it's a bad load. You don't have to dig much deeper in it. You can, but you don't have to. Parallel circuits are the ones you're going to most commonly find in the HVAC industry. These are the circuits that do the work. All loads in a parallel circuit receive full source voltage. That's the difference from the series circuit. Series circuit, they split the loads. In a parallel circuit, all loads receive full source voltage. Parallel circuits exist when a circuit has more than one load, but none of the loads receive voltage from another load. If one load burns out or goes bad, the remaining loads will continue to operate. All loads get full source voltage. The total amperage of the circuit is the sum of all the amperages. In other words, each load has an amperage, creates a current. You add them all up, that is your total amperage of the circuit. The total resistance in the circuit is less than the lowest resistance on any branch in the circuit. This is a parallel circuit with two loads, okay, and one switch. That switch closes, you're going to get full source voltage to loads B1 and B2. This is an example of two loads in parallel, each one controlled by its individual switch. I can energize B2 with switch 2 without B1 being energized. Okay? Again, amperage adds. This is the most common circuit parallel in an HVAC industry. Troubleshooting parallel circuits, same basic procedure. Start at source. First, make sure all the switches you can control are closed. Check your source. Check voltage between L1 and the start of the branch. By the way, each one of these is considered a branch. It's like a tree. You start at source, then you branch off. Check voltage between L1 and the line side of switch 1, load side of switch 1, line side of B1, and load side of B1. Okay? Once again, across the load, I should have full source voltage. It's a parallel circuit. Check voltage on the next branch. Notice my left-hand side of the meter has not moved. That's clamped on. Continue to come through here just like you did. And again, second load, even though it's energized, okay, you will get the full source voltage on both loads. Any switching device with an open will read 0 or will read 120 volts, full source voltage. If the switch is closed, should have 0 volts. You should read full source voltage across a load. And if the load gets full source voltage and is not running, you have a bad load. So again, when troubleshooting a parallel circuit, if you get source voltage across any switching device, that switch is open. When you troubleshoot a parallel circuit, if you get source voltage across a load and that load is not operating, the load is bad. Troubleshooting rules always apply. Start at source and work your way from there. If you get any voltage across a switch that is open, okay, or bad. If you get a voltage at a load and the load is not working, it has failed, replace it. Just a few extra notes. When you're working with a meter, be very, very careful about where you're putting your hands and be very careful on how close together you're putting your meter leads. Especially the metal ends. They can arc and they can cause a short circuit. Okay? If you touch one meter lead to voltage and touch the other meter lead to the case of the equipment, that meter lead is live. Okay? You could really get hurt by voltage being on that case. So again, just be very careful where you put things and where you put your hands.